Hello students, so today we are going to study about the groups, vector spaces and vector subspaces. Alright, the first part we will see about the groups. So what are groups and how you should define it in the later part. First we'll see in the general scenario. So the group is like you're hosting a party and the party is divided based on the interest of the people and the personalities, right? Interest and personalities, right? So when I so that people shouldn't be bored, and like-minded people are hosted together. So when I talk about the mathematical perspective or the computer science perspective, the science perspective, I talk about the mathematical objects which are called as sets. Say set of 7 red balls, sets of 8 red balls, like that. So where we can use this group, so groups could be used in cryptography, they could be used in encoding or sending the messages, sending the message safely to the recipient, or you can use it in the graphics also. So without further delay, we will move to the definition part and what the definition tells. So the definition is, so let's talk about the definition now. Now consider a set G and an operation that is the tensor product group cross group that should belong to the group defined on the G. Then G is equal to that group comma, and the tensor product is called the group or in the following hold. So there are 4 conditions that has to be met. There are closure, associativity, neutral and inverse element. So when it comes to closure, it is just a simple addition. 2 plus 3 is equal to 5, where any addition gives the product will be belongs to the group. Then we have associativity, where we consider 3 elements x, y and z, and if I take the example as 1 2 3, and if you multiply or add in first 1 and 2, then 3, or 2 and 3 first and then 1, the answer will be the same. Hence whatever the answer you get, it belongs to the group. Then comes to the neutral element. Suppose you add any say 0 to any element, say 1. So 1 plus 0 will give you the answer itself, that is 1 itself. Therefore any element or the neutral element, say 0, also belongs to the group. All right. Then the last but not the least, the inverse element, say x minus of x, or x of x of minus x, answer is 0. Therefore inverse is also say it belongs to the group, so therefore 0 belongs to the group. Now so let us see the vector space. So we have a real valued vector space V with a V as a set comma plus and scalar multiplication. So this plus and the multiplication has 2 conditions, where for addition, if you multiply 2 vectors, you get the vector itself, and for the multiplication you have to multiply a real number and a vector, then you get a vector itself. So this is the definition of the vector space. Now here there are 4 conditions that you have to see. First one is abelian group. That means if you add any 2 vectors, then you get the vector itself, which is said in the first that is the first and foremost condition of the definition. Then it comes to the distributivity. Distributivity is nothing but, if you have already studied about distributivity, and this can be applied for addition and multiplication, and you will get the same answer. And the last but the third one is associativity, where you can apply the associativity to the three numbers, and the multiplication will be the same. Last but not the least, to have neutral element. If you multiply 1 with any number, you get the number itself. So those are the 4 conditions for vector spaces. Now let us see about the vector subspace. Instead of directly going to the definition, we'll dissect the definition first and then we'll go to the definition. So first we know what is vector. Vector V is nothing but it is a vector which has n number of vectors, say v1 v2, say up to vn, right? And we know that the operation that could be performed to the vector V is nothing but it is the addition and the scalar multiplication. Now let us see what is vector subspace. What is vector subspace? Now it is indicated by the letter U, capital U, and we can also say that this vector subspace, as in the name, it is nothing but it is a subset of V. Okay, how we'll write subset of V, right? Suppose say U has, say, vector V1 and V2. Say V1 and V2, and I can say that this V1 and V2 are from the main set V. So I can say that V1 and V2 are included in the main set V. Right? Can I also say that U is nothing but it doesn't have, it might not contain all the vectors in the V. It has only limited number of vectors which is there, which is required for the subset, right? So I can say that v1 v2 are the only two elements it is there, and it doesn't contain all the elements from the V. Now let us go to the operations part. So what is operation? When we talk about U as a vector subspace of V, it means that the operation of addition and scalar multiplication is defined on V are also defined on the U. In other words, we can perform this addition and scalar multiplication on the vectors within U just like we do for the vectors in the V. So can I say that if when I say it is a subset, then I can say that the operations are also included, that is plus and multiplication are also included in the U. Now let us go to the definition part. So let's read the definition. So let V, which is nothing but vector space, and U is a subset of V. U is a subset of V, and when I say set, it shouldn't be equal to null. Then U is equal to, when, so what is the last one I said? Operation. So whatever is included in V should also be included in the U. That is why U comma addition comma scalar multiplication is called vector subspace. So that is all, guys. So I hope you like the video. Thank you.